hello everyone. Welcome to today's virtual training session. And my name is Dan Painter. I am the Product Training and Development Manager at Flintwalling, and I will be conducting today's broadcast. Today's broadcast is entitled Submersible Pumps and Motors. I see that we still have quite a few people coming in that had previously registered, so I guess before we get rocking and rolling with this, a couple of notes up front. Next month, and if you check our schedule, our web conference schedule on our website, next month there are a couple of new presentations I'm going to be doing. In fact, on the 1st of March, I'm going to be doing a presentation entitled House of Resistance for Subs. Again, House of Resistance was put together probably 8-9 years ago, and it was designed to assist people in sizing above ground pumps like centrifugal pumps or jet pumps, things of that nature, for small residential homes and or irrigation systems. So if you've ever attended that presentation, it's it just makes pump sizing a lot more understandable. More importantly, I think it's something that's a lot easier to retain. And so we will be doing House of Resistance for Subs a couple of times. You'll have a couple of shots at it next month, like I said, beginning in March. And then also in March, I'm going to do a presentation strictly on submersible pump and motor troubleshooting. In other words, how do we determine what caused the problem, or what is the root cause failure? I know there's not a lot of repairs made out there anymore. So much is just simply replaced. But that said, we still have obviously a need to be able to have skills for troubleshooting these products. So, and then the last of the little gibberish I'm doing up on here prior to starting this, on your dashboards, there is a tab called Handouts. And you don't have to do this now, and I'll leave the slides up at the end of this presentation for a period of time, but there are a couple of PDFs up there that I uploaded earlier today. One is basically it's going to cover a lot of what we're going to be talking about in this presentation. It's a 4-page brochure. I think it's entitled Why Buy Flintwalling, but in there are all these various components that we're going to identify today, as far as the materials of construction, their functionality, and what they're supposed to do. We're going to take a very swift ride from the very top of this pump all the way down to the bottom of the motor. Speaking of the motor, I attached what's called a motor application guide. So that's another PDF that's up there that you could download if you'd like. And it's just technical data in regards to a 4-inch Flintwalling motor. There's also a survey out there, so if you feel kind enough to give us some feedback on how we're doing with these things, we always appreciate getting those as well. So with that, I see we're about 5 minutes after the hour. We're going to go ahead and get started. Again, we're going to be talking about submersible pumps and motors, and we're going to start at the top up here. I'm going to bring my highlighter up so that hopefully you can see it on the screen. And like I said, we're just simply going to work our way from the top all the way down to the bottom. And we're going to try to do that. I got about 30 slides to share, so if I spend less than a minute or two on each, we'll knock this off in the next shortly less than an hour. What you've got shown on your screen right now is a discharge. In that discharge, there's a couple of components. The one we'll talk about first is what's referred to as a check valve. I have a lot of opinions on this check valve. I sold submersible pumps back in the mid-'70s, and I sold a lot of different brands back in those days. And sometimes when I'm giving tours, I'll tell contractors, I said, when I sold submersible pumps back in the 70s, I never, ever, ever had a check valve failure on any of the brands I sold. Everybody looks at me kind of funny, like, well, what are you talking about? And I said, well, back in those days, at that time frame, pumps didn't have a check valve in it. It was up to you, the installer, to determine what type or where you wanted to locate a check valve in that water system. Given the fact all water systems need to have check valves, somewhere along the line, somebody somewhere got the idea that if they could build it into the discharge of a pump, That might save a contractor money, and it might save him time on his installation. So when we look at these check valves, I'm only going to spend just a little bit of time down. This is the current check valve Flintwalling's got. I believe it to be a pretty daggone good one, and I'm going to explain why. But I also at the same time tell you, stay tuned. There's some even greater improvements coming, and there's just around the corner. So down at the bottom of this check valve, it's a two-piece. There's a guide. This is a guide here that my cursor's circling around. That threads into the top of the discharge. The poppet has a tapered bottom, as you see, and that tapered bottom is so that when that poppet comes up, when the pump fires up and is pumping water and then shuts off, we want to be able to kind of self-center that poppet back down into this sealing area here so that that O-ring and these sealing surfaces make a watertight seal there, or a seal there. The top of it's capped off. That's an improvement that was made several years ago, really. The old guide, the poppet used to come right up through the top of the guide. But this is capped off, and the reason we cap this off is, I'm going to be straight up with you. And in my career, I had the opportunity to travel this country coast to coast for many, many years. And there were a lot of states I went into, and my opinion was, you drill a well in this state, you're probably going to have sand. I mean, that was just the opinion I had, and a lot of contractors in that state would, debate that with me. Painter, I screen my wells, man. I don't have any sand. And so one time I was on a job site, and the contractor was telling me, he said, my wells don't produce sand. And I said, well, let's go check something out. We walked into this house, walked into the bathroom, took the flush tank lid off of the flush tank of the toilet. And I pointed down in the bottom of that flush tank, and I said, so where'd all that come from? There must have been an inch and a half of sand sitting in the bottom of that. The guy looked at me. He said, dude, that's sugar sand. That doesn't count. I go, what do you mean it doesn't count? He said, it's real fine. He goes, it doesn't plug anything up. It doesn't plug aerators up in the faucets. But that all said, you see that snow globe over there? That's, a lot of kids like to have these like souvenirs. You see them all the time. You shake them, set them down on a table, and for the next 30 seconds, you can watch all those little sprinklies resettle to the bottom, and you can do it all over again. Well, if you're pumping sand in a well, it's really no different. Once that pump shuts off, any of that sand that's in that drop pipe is going to want to slowly settle back down, just like the snow globe. So what we didn't want is any of that sand to get between that guide and that stem, so we just capped it off. So that's not even a concern of ours anymore. If it's the only check valve you have in your system, and I'm going to tell you something, Flintwalling, and I believe every one of my peers in reading their instruction manuals, and some of us do a real good job, perhaps, than others in burying this in the text somewhere. But every pump company is always going to recommend an external check valve in addition to the one that they ship that's already built into the discharge of the submersible pump. They always recommend an external check valve because it's very important that if the check valve in the top of the submersible is the only one in that whole system, it better seal so that when that pump shuts off, that'll hold that column of water in the discharge pipe. The last thing we want is for that check valve not to seal and then allow that water to come running back. You're going to pull a vacuum way up the top, so on and so forth. So the recommendation is an additional check valve. And that's everybody. That's not just Flintwalling. That's everybody we compete with. They all ask that you add additional check valves. And here's the reason why I believe. If you ever saw the water coming out of the discharge of a pump, that water is spinning at about the rate the motor's turning, right? So the water coming out the discharge, right here, right at the discharge, that water's just come through this whole stack of impellers. They're all sitting in there spinning at 3,450 RPM. So you can only imagine what that water might look like coming right up through that discharge. It is a very, very turbulent environment. So one thing that we've done with this check valve here, and like I said, we've got some really good enhancements coming here just around the bend here, not very far down the road. You see this is a rectangular stem on the top of that poppet. This guide has a rectangular opening in it. So when you push that rectangular stem into a rectangular opening, obviously you can no longer spin it anymore. So it becomes anti-spin. And that's not how they all work, but that's how this one works. And the last thing we want is to prematurely wear out a check valve. This is a shot we took in the lab one time, and we drilled a hole in the discharge, so we could actually see what that poppet was doing when this pump was pumping. In fact, this pump was just simply pumping open discharge. So this is a very quick, I don't know, 3-4 second video clip. But if you'll notice, the lab technician put a permanent red line on that little cone portion of that poppet. So just kind of focus on that red line there as I fire this video up. So there's no sound coming with this at the moment, but that pump is running, that's a 19 gallon a minute, 3/4 horsepower, and is pumping at full open discharge. But you notice that poppet, you know, it didn't sit there chuck, it didn't move back and forth. It was very, very stable. So that said, I believe we have a very, very stable component in a very unstable environment. The next component down from the check valve is what's referred to as a discharge bearing. We typically will use what we call a no-lead bronze closed discharge bearing. If you're not using a closed discharge bearing, then you're going to use a sleeve bearing of some type. More than likely, the team here at F&W, we opt to go with the one obviously over there on the left-hand side, because we don't believe that a sleeve bearing is watertight. We believe water can and will pass between the bearing and the pump shaft. Now, you know, is that a big deal? No, I don't think it is, unless, what if you got that daggone sugar sand, sir? You said that was fine, right? You mentioned to me that that was really, really fine. Is it possible that we could also run some of that garbage between that bearing and that shaft? Because if you can run abrasives between that bearing and that shaft, and you prematurely wear that bearing out, you will replace the pump. And that's not maybe, that's the only bearing. That bearing supports the entire pump stack on the wet end or the pump end side of this pump and motor assembly. Obviously, with a closed bearing, no water can pass through there. And I guess if that logic is it holds, if no water can go through there, then obviously there's no place for any sand or abrasives to go through there. And so that's why we actually use this same bearing on our centrifugal pumps at the very end of the centrifugal pump. So it's a bearing we've got a lot of confidence in. It has withstood heat, abrasives, all kinds of things. So that's the discharge bearing. But that's where other discharge bearings that are used in the industry, I mean, not all pumps are alike. Some use a rubber. That's that one on the top left is very, very pliable. You can squeeze it with your index finger and thumb. The one just to the right of that's a closed bearing, but it happens to be made out of a plastic material. And then the one bottom right is a ceramic bearing. And ceramic's a great material. I used it in my prior life, prior to pumps. I was in the water treatment industry for, I don't know, 20 years, 25 years. Ceramic is a very smooth material. It's a great sealing surface. It's very, very hard. It just doesn't like temperature changes, if you get temperature changes. And so there are times where, you know, as no fault of any of us, we can end up in situations where these pumps are either deadheading, which is, you know, essentially a pump pumping against a closed valve, which is very, very destructive, or they're in a run dry situation, and in either case, they're going to get a lot of heat rise. And so we've done some in-house destructive testing. We've ran that submersible pump of ours dry for 4 hours, and that's what you're looking at. That image, the top left, that's what that discharge bearing looked like after a 4-hour run dry. We didn't fare so well with the other closed bearing because it was not made out of a material that would withstand heat. It went about 46 minutes, and then you can see what happened is it melted down. Same with the The rubber sleeve bearing, it also, again, wasn't designed to take heat, so in less than an hour, both these pumps were shot. And as I mentioned, that ceramic bearing got a lot of great attributes to it. However, it doesn't like heat. What will happen is you'll get a hairline crack down the side of that bearing. It'll be like a fracture. It's just a hairline fracture. But when that happens, that bearing's shot. So again, we do a pretty good job, I think, when it comes to discharge bearings. All right, we're going to move down into the pump end itself. The submersible pump end, when we look at the components that are inside of it, obviously they're going to be diffusers. Everybody's got a diffuser of some type. What we call a thrust washer. Some people call it a thrust bearing. That's that little gold washer you see on the hub of this impeller. On the bottom of the impeller is the eye down here, very large eye. And on the top of it is the hub, and this thrust washer sits over that hub. And then at the very bottom that kind of sandwiches everything together is a diffuser plate. So again, when these are all sandwiched together, assembled together, they look similar to that image over on the right-hand side of your screen. And that's simply referred to as a stage. Whoops, I kind of sped through that a little bit there. There we go, stage. That's referred to as a stage. And submersible pumps will have various stages, right? We make some deep set pumps that'll have, 30, 40 or more stages because they have to be set so deep in a well. Imagine a well that's 800 feet deep, and you put a pump down that well. How much pressure is that pump going to have to produce just to get the water to the surface, So it takes a lot of these stages. And I think here in another slide or two, we'll understand why adding stages adds pressure. So when a pump's up and running, we all know that water is going to enter a suction screen right dead between the pump end and the motor. There'll be a suction screen where the water will come in. And as that water comes through that suction screen, it will travel up through however many stages are in that pump end until it discharges right out the top. So let's look at what happens inside of here, all right? So we've got this water coming through the suction screen. The very first thing it's going to do is it's going to go into the eye of the very first impeller down here. So it's going to go into the eye of that impeller. So what happens then is as that water's coming up, it enters that eye. And as I mentioned early on, this impeller is spinning at about 3,450 RPM. So it's moving like it's very rapid, all right? So if you had no diffuser that come down over the top of that impeller, this piece right here, if that wasn't down over the top of the impeller like it is in the stack, that impeller would be shooting water out there 30, 40 feet. What that impeller does is it takes that water that's being fed to it through the eye, and it creates a tremendous amount of velocity, right? So that water would be just shooting straight out of that impeller. However, because it's encased in this diffuser, that water obviously can't just shoot out there arbitrarily in both directions or all directions. It's going to go right into that diffuser. And if anybody ever asks, and we've all heard that term diffuser before, and if anybody ever asks, well, what does it do? That's a very easy thing to answer. A diffuser takes the velocity created by the impeller and converts it into pressure. And therefore, the more stages we have, obviously, the more impellers and the more diffusers we have. And so as this water travels up this pump end, each impeller, each stage that it goes through will continue to add more and more and more pressure. So that's what you get by adding impellers to a submersible pump end, is you give yourself the ability to generate a lot more discharge pressure coming out of that pump. And then that will just continue right on up through the stack until it reaches the discharge. I want to talk about this thrust washer. We mentioned that just a second ago, and if you ask, well, what's that for? Well, thrust bearings are put in a submersible pump end to compensate for what's called upthrust conditions. And I know some of you out there have heard that term many times in your career, you know, up thrust. And so for those of you that may not be quite as familiar, if you want to know what that is, the description's on the screen. It is a sudden and forceful upward movement. That's what describes up thrust. Well, let's look at those two words, sudden and forceful. Sudden, all right? Well, that motor that's sitting on the bottom of that pump end will reach full RPMs in about 0.4 of a second. So that's almost the blink of an eye. So we go from 0 to 3,400 RPMs just in a blink of an eye. And so that's pretty doggone sudden. And of course, it's running a pump, and that pump's trying to do what? It's trying to move all that water upwards. And so that's where you get what's called up thrust. Now, when you get up thrust, there's some, it's because there's no, I'm going to bring that animation. That's because there's no head pressure against that pump. The minute you put that pump in the well for the first time and you fire it up, it's going to be an up thrust. Because you've got a discharge pipe that needs to be filled. You've probably got a pressure tank up above somewhere that's going to need to take that water and pressurize. And until that, you start to see back pressure against that pump end, all those impellers and diffusers, they want to come right out that discharge right along with the water. You're going to be in up thrust anytime you are in what's called open discharge. And I know, having traveled this country for so many years and being out on jobs with a variety of well drillers across the country, I found that not every well driller develops a well in the same manner. So once they drill a well, it's very common that a driller is going to have to develop that well. And I think what they are talking about there, or what that term refers to, is all that drilling mud and all that shavings. They need, you need to pump all that stuff out of the well. You're not going to send that into someone's house. And so a lot of times they'll do that by just simply letting the pump open discharge out across the grass or the driveway somewhere until that water starts to run clear. Well, again, this pump that you see right in the center here that's down that well, it's in up thrust. And I don't care what brand it is. If it's mine, it's in up thrust. If it's any other brand, it's also going to be in up thrust because there's no head pressure. There's no pressure, coming back to kind of hold everything down in place. And so that's what's called up thrust. And I've got opinions on that too, I think anytime you place a pump in the well for the first time, you're going to be in up thrust. I think anytime you're pumping open discharge, you're going to be in up thrust. I think anytime a pump is not sized properly, in fact, a lot of these deep set pumps, if they're not sized properly, and I just know for a fact that we have some deep set pumps out there that have been in up thrust and will continue to be their whole life, right? That's just because they were not sized properly to begin with. And over there on the right-hand side of your screen are some varieties of thrust bearings or thrust washers that I've found in the industry. Flintwalling's, I'm pleased to announce that we're open for tours and training events over these winter months. And so when people come to our factory, they get to see these things manufactured. So we stamp our own thrust washers out along with a variety of other things. So anyway, moving down into the impellers, Flintwalling's always had what they called a floating stack, and I want to explain to you what that means. So if we look at this impeller diffuser assembly over here on the left-hand side, this impeller is sitting inside the diffuser. There's the thrust bearing and thrust washer. This white piece on the bottom's got a large ridge around it here and here. That's the bottom diffuser plate. So when the pump's off, this impeller is going to be riding near the bottom of this diffuser plate right here. All right, that's where it will be riding, near the bottom of that. When that pump fires up, that pump comes on, and it's pumping for the very first time, and it's pumping open discharge. Everything wants to rise up, and so that's where that thrust bearing comes into play. All right, and I've watched a guy develop a well. I watched him put a pump in a well and pump that thing for 2 hours, and for 2 hours, trying to clear that oil, that pump was in upthrust. And so you better, if you're going to be in upthrust, you better have a bearing system or a washer system of some type that's going to withstand that. We manufacture all of ours out of stainless steel, and I'm not sure everybody does. In fact, that previous slide is evident that not everybody makes these components out of the same type of materials. But that's what happens when you're in upthrust, all right? Now, the floating stack. All right, the floating stack is such that, and I don't know how many pump companies make this claim. I don't know. I do know that I can state that these plastic components, the impeller, the diffuser plate, all these plastic components that make up a Flintwalling pump end are manufactured by our own plastic injection molder. It's part of our divisions that we have within our family of companies is our own plastic injection molding. And so many of the plastic components that you'll see in a Flintwalling pump are self-manufactured by our own company. So one of the dimensions that we're going to take when we bring these impellers in, because they are, is this dimension right here. All right, from the top of the hub down to the bottom of the eye. That's got a tolerance that range that it will accept it. All right, but if this happens to be just 1/1000th of an inch shy, or something, 1/1000th of an inch shy, something like that, no big deal, no big deal. But if you start to put 15, 20, 30 stages in a pump, those all add up. And so Flintwalling will take these measurements. They'll measure this section right here from top to bottom, and we actually, we'll actually build a pump up, and we'll build it one stage at a time. And every stage that we add, we put 400 pounds down on it to read what this variance is. I don't know that I'm explaining this very well. Let me try to get to this point. See that little washer here? We will shim our pump ends. We'll shim them to compensate for that little thousandths of an inch shy, and we don't want all that adding up. And the reason we don't want it all adding up is because when our pump is up and running, it is designed so that when it's sitting there running at full RPMs, this impeller is floating inside of that diffuser. There's no rub at the top. There's no rub at the bottom. That's why we put this ridge on the bottom of our diffuser plate right here that I've got my cursor on. It allows this impeller to move up and down, and still we have that engagement of that water coming into the eye of that impeller, whether the impeller's sitting down lower or whether it comes up higher. But that impeller is designed so that when it's running, nothing is rubbing against each other. It's floating within that diffuser. I know this is going to sound a little salesy, but in my career, I've had so many contractors come up. Flintwalling, man, they make a pretty doggone good. We don't have to work on very many of those. They last a long time. Yeah, they do. And these are some of the reasons why. They know they last a long time. They don't necessarily know why. When it comes to sand, looking at sand, again, we do a lot of destructive tests up there at F&W to see how we compare with our peer group. And so here's a couple of impellers, and that you can see this top one, it didn't fare so well in our sand testing that we did. You can see how the sand eroded away the material on that impeller. When the test was complete, the performance was nowhere near where it would have been had that pump been brand new and you take that performance. These are non-clogged impellers. They're used a lot of this style of an impeller is used a lot in sump pumps. They're non-clogged, but you can still see what happened in a sand environment where the sand just literally cut grooves around that impeller and actually distorted the eye. And there's ours. We got a little slight rub around the eye of our impeller, but that's it. Just that slight rub right there. That didn't change the integrity of that impeller. It didn't change the performance of that impeller. And so once we concluded our sand test, unlike the two above us, we were putting out just as much water in our post-test as we were putting out in our pre-test. And again, that rub is around the eye of the impeller. The thrust bearing that we talked about earlier goes around this hub. So that's there for the upthrust, not that sand. So that's all we got right there, is that little bit. So we're going to move on down. I want to talk about this staging just real quick. And this is an opinion, but in my opinion, there's pump companies out there that have de-staged their pumps, and I'm all in on that because I've seen the catalogs, from the 70s and 80s and up to now. They've taken a stage or two out. I don't know that benefits anybody but their stockholders, but here we are. We always will state how many stages are in our pumps. This happens to be a performance curve for a 7-gallon per minute pump because I see every one of these sweet spots are landing right here on that 7-gallon per minute line right here. And so you take a half horsepower Flintwalling pump in. It's going to have 10 stages in it, right? 10. Well, maybe our competitors only got 6 or 8 or 7, They'll still hit this sweet spot, but don't ask anymore. If you ever find yourself having to go left of this, on the left-hand side of this curve over here, that's where you're going to find these additional impellers. Or not additional impellers, the fact that we never took any out maybe would be better stated. That's where that shows its performance. And again, if you've miscalculated your total feet of head, you take this pump right here. This is a 3/4 horse, 14-stage pump, all right? So at roughly 335 feet, looking at that, about 335, you're getting 7 gallons a minute. What if you miscalculate? What if you're at 400 feet? Well, 400 feet, we're still giving you water. Well, this guy, oh no, you're not going to get anything beyond that. So you 400 feet, you get nothing there. So that's where that staging comes in. All right, I'm looking at, we're down at the bottom of the hour. We're going to move on down to the lower section of the pump and motor assembly, and we're going to go into the motor itself. And again, if you've never been to our factory, I'm extending a personal invitation. I am the tour guide. I give the tours and do the training up there. And I instead of telling you, showing you this, you actually see it for yourself. When you come to F&W, you not only get to see the pumps manufactured, you get to see the motors manufactured as well, starting off with the shaft and spline. We have a piece of equipment up at Flintwalling called a hobbing machine. It's awesome to watch. It's what cuts this spline into this stainless steel shaft. It's pretty cool. It's a really, really, you've seen threads cut before, but to see these splines cut, I just find it fascinating. But that's very, very important. We spend a lot of, we pay a lot of attention to detail here. That spline is what's going to engage with the pump coupling that's on the end of the pump shaft. So you don't want too tight or too loose, too deep or too shallow. You need to have a very good engagement here between the spline and the pump shaft coupling. Just below that's pretty standard. It's called a sand slinger. I think you'll probably find this on most submersible motors. Go back to that snow globe thing again, right? So if you got a well that's producing sand and you get this settling of sand coming back down, the last thing we want is for any sand to get down into where I have my cursor on. This is called a lip seal right there. That's what seals that shaft coming out of this motor, all right? That's what seals it. So we don't want debris getting down in there and damaging that seal in any way. And so that's why this sand slinger is on the top of the shaft. It acts as a shield to kind of slough all that off so that nothing gets down into the lip seal area. I will be circling back on this lip seal here in a few more slides, something we learned about during our design and development stages back in, 06, 07, somewhere in that area. So we're going to move on down to what we call our stator end bells. And we opted in our motor to go with stainless steel. Not everybody does. And we have another destructive little test that we do up at Flintwalling. This was called Instant Ocean. We took a very large aquarium and dosed it with sodium chloride salt, but dosed it real heavy to the extent, we were at about 40,000 parts per million of sodium chloride, and that was a whole lot like seawater. All right, but if you don't have stainless steel in your construction of the motor and these kind of corrosive environments, it'll start to show its face. And I don't know of a contractor, one, that hasn't told me they've not seen this on the left-hand side occur before. And so when you pull a motor out that looks like that one on the left, you either got an iron-bearing water supply, which that could be the case, or you've got a corrosive water supply that's starting to affect some cast iron that's below this stainless steel sheath here. But nonetheless, we opted to go stainless steel, top and bottom. I want to take this end bell. I'm going to flip it upside down. This is the end bell here. So it's welded. Obviously, it's laser welded into the motor shell. But prior to that, take it out, flip it upside down. This is what's located on the bottom side of this upper stator end. Okay, so what do we got up there? Well, we've got some lightning arresters, those little gold thimbles. I can tell you right now that what we're looking at is a 2-wire motor because there's only 2 lightning arresters. Had this been a 3-wire motor, this vacant socket over here would have held that 3rd lightning arrestor. So again, this is a 2-wire motor. This is the lead socket. So this is where your motor leads are going to plug into from this side, what would ultimately become the top side. But when we talk about attention to detail, our assembly crew actually will put a bead of sealant around that lead socket because we do not want a leak path for any water to be able to get inside of this stator end. So they'll seal that off. Over here is what's referred to as a 2-wire switch. Not used anymore in Flintwalling motors, but in the early ones, when we first came out with our motor several years back, we opted to go with the 2-wire switch. There were some challenges with that. If you look at the screen, picture on the top right-hand side, that inside this, what looks like a thimble, is a set of contacts in there. And so those must open and close at the precise moment because that motor has to go from the start windings into the run windings, and those contacts are what makes that happen. And if they don't break at the right moment, then you end up hanging up in the start windings, you end up with high amps. We had to calibrate every one of these things. We had to calibrate them, and those contacts operated off of current, i.e. heat. And so heat is what opened and closed those things. And it was very laborious for us to test these out to the extent we were comfortable that we could put it in a motor and have a good product. And it was very, very laborious for us. So what we're using today and have been for some time now is what's referred to as an electronic start circuit. And this thing, I happened to be at the South Atlantic Jubilee in Myrtle Beach back, I believe, last August. A lot of contractors there, a lot of 2-wire pumps sold in that market. And I was asking the contractors, how's that new electronic start circuit working for you? They were just, they were thrilled. So, some of the things here, precise trigger point, this switch here, it's voltage controlled, okay? So it doesn't rely on heat. There's no moving parts. It's solid state. So we don't have strips moving back and forth to make and break contacts, all right? It's these are manufacturing repeatability, exceptional quality control. So this thing has just made life so much better on our 2-wire motor and with our 2-wire motor customers. It just brought a whole lot of advantages to the table. It's manufactured in the USA and it's 100% tested. Here's some of the, it's had over 250,000 on-off cycles. We've misapplied line voltages to see how it would react in those situations. And bottom line, after our intense field testing was performed all across the country, the results were actually less than 0.5% failure. And so the confidence level is very, very high in that electronic start circuit. All right, moving on down into the area here of the motor. When I'm giving tours, there's a section of our motor manufacturing facility, our submersible motors, and I'll stop and I'll look at the contractors and I'll say, now y'all know these submersible motors are all water cooled, right? Well, they look at me and go, dude, we've known that for, yeah, why would you ask us such a stupid question like that? I said, well, do you know that water can and will at some point get inside that motor too? And that's about the response I get. What are you talking about? Well, let me show you. This is what's called a rotor liner. It's a stainless steel tube, and it's very thin, very, very thin. But it's laser welded up here at the top and down here at the bottom. And so it just creates you can look right straight through there and see nothing but the inside of this tube. All right. And that's where the rotor sits. That's where the rotor sits. Now, we die cast our own rotors. If you've never seen this process done before, you probably will when you come to our factory and take a visit. We take these rotor lambs and we'll weigh them out. We know how many of them make up a certain horsepower. They stack up on top of one another. And so they'll know how many of these it takes to make a half or a 3/4 or a 1 horse. And they'll stack these all up. And then once they've got them stacked up, they will pour molten aluminum. And that's what die casts that rotor. And it ends up pour molten aluminum down into a mold. And it will die cast that rotor and send an electrical grade aluminum down through every one of those columns like you see here. All right, so that's what's called rotor die casting. And then once we've done that, we will balance those rotors 100%. This rotor has to spin at 3,450 RPMs inside this liner. And we do not want that rotor striking that liner anywhere. The result of something like that happening will be catastrophic. And so we balance every single one of these rotors prior to putting them in a submersible motor. We'll talk about the encapsulation here a little bit. I'm looking at the clock. I'm going to be right on time, I believe, with this presentation. But this encapsulation is this black material that you see here, all right? We spent a lot of time on encapsulation and how to do that. Basically, what encapsulation is going to do is it's going to encapsulate all these stator windings that you see. And again, all this is on the outside of that tube. So everything on the outside of that rotor liner, everything on the outside of it is going to be encapsulated. This comes in as a kind of a slurry. It cures and hardens. It becomes very hard like that. Encapsulation is very, very important. I happened to be walking a trade show one day and an open house or whatever. I can't remember what it was, but you go to these shows and a lot of manufacturers bring their wares in the form of cutaways. And I happened to walk past this particular motor. It was a cutaway motor, but if you look at it, there's the encapsulation. There's a little lighter in yellow in color, and of course the darker is is the stator winding. This was taken with a cell phone, probably pretty quick. But I'm pretty certain what I saw when I looked at that motor, I'm pretty certain, and I'm not saying this boastfully, I'm only saying this because I was around when we were designing and developing our own. I saw something I'm pretty sure no other contractor would have seen. In fact, what I saw, I don't even think the people that were displaying this had any idea. Here's what I saw. I saw air pockets, and a lot of them, in that encapsulation. And I brought this photo back and I was showing it with our engineering team. They said, oh boy, that's not something we want. We spent a lot of time to avoid that. And I said, well, and so we do have a bit of a proprietary method of bringing encapsulation into our motors so that we don't have these air pockets. Guys said that probably is going to be problematic at some point. And I said, why? He said, well, if you understand what encapsulation's primary purpose is, it's to dissipate heat away from those windings. That's what it does. It dissipates the heat, allows the heat to dissipate away from the windings to the outer shell of the motor where the water carries it away from there. And he said, if those air pockets, he said, the problem I've got is those air pockets are going to heat up a lot faster than anything else, and they might have the ability to start expanding. And if you expand those air pockets too much, you lose this ability to dissipate that heat. Well, obviously, you're going to kick out on thermal overload. So here's a cross section of a Flintwalling motor. So inside is that rotor I showed you with all that molten aluminum die casting through those columns. You can see how close that rotor spins within that liner. That's why that balancing is so important. And then the next stage out is our stator, and that's your stator windings going around here. And it doesn't matter where you would slice this motor, this is what you're going to see every time, and there are no voids, no air pockets. It's solid. It's just as solid at the top as it is at the bottom. So it's top and bottom solid there. In that column there, where that rotor liner goes, is fill solution. And most all motors are going to have a fill solution that'll encapsulate that rotor right there. So this area here, or inside this motor, is in a liquid, right? It's in a liquid. And this fill solution, we spent a lot of time on because it is a recipe. And so I'm going to tell you, we spent 9 months on it, on that recipe. But one of the things that we found in the design and development as we continued to tweak this fill solution was this. We found that we were able to get this fill solution tweaked out to the extent we were not seeing any lip wear whatsoever when we would do audits on field testing that we had done. We'd bring pumps and motors back. We'd tear them apart. We'd inspect the wear patterns and compare ourselves with our peer group to see how were we faring amongst our peers. And we were getting absolutely no lip wear whatsoever. This is I gotta move my dashboard out of the way. This is actually an excerpt out of an engineering report that came back. It was a 24-month audit. 2 years, this pump had been in the motor, had been in the well. And when they were doing the lip seal evaluation, they had no lip wear, no lip wear at all. And obviously down below was a note in regards to that fill solution ratio that I mentioned. I'm not going any further than that, but I'm just telling you that we spent a lot of time on that fill solution to achieve some of these objectives here. All right, moving to I believe the last of the components here, and I think this is one of our strongest points, quite frankly. It's referred to as an axial bearing down at the bottom. Some people call it a thrust bearing. Some people call it what do they call it? Like a Kingsbury or a Kingsbury style bearing. But this is what it looks like. There's a carbon bearing that sits down on these segments here, these chutes, all right? An F&W motor today has a 750-pound thrust bearing in the bottom of it, whether it's a half horsepower or whether it's a 2 horsepower. All of our motors are being shipped with 750-pound thrust bearings. Now, in classrooms sometimes, I'll ask contractors, I'll say, have any of you in your career ever come across a pump and motor assembly where you've lost that bottom bearing in your motor, that thrust bearing? And all these hands go up. I think it's not every day, but they've all had the occasion where they've lost that bottom bearing. This is not a picture of a Flintwalling bearing. This is simply a picture of what that bearing would look like. This come out of somebody else's motor, but you can see the carbon fractured. Not all the segments are there. That bottom bearing is where the buck stops, right? That's at the very, very bottom of that motor, and that's where all that thrust is coming down to. It's right here. And so that's why we use that 750 pounds. But most people will know whether they lost that bearing or not, because if they do, more than likely that shaft will drop. It'll drop slightly. Now, when that shaft drops, it becomes disengaged or partially disengaged with the pump coupling above it, and now you just start tearing up everything, right? You'll strip out the coupling, or more than likely, and now you got a motor spinning and nothing else is happening. Very, very easy to tell whether you've got a damaged bottom thrust bearing or not. These things are a dime a dozen. I think every motor manufacturer supplies these. It's called a shaft height gauge. And so when you set this shaft height gauge on a good motor, You set it down on top of that rotor shaft spline up there, this thing ought to swing back and forth like a porch swing. It ought to swing back and forth. But if that shaft's dropped, and you put that shaft height gauge on there, and it won't swing. So that's your indication that shaft had dropped, and now you've got a bottom bearing that's no good. But I'll say this, and I'll leave you with this too. In classroom, a lot of times I'll ask the question, hey, any of you all ever been to Gatlinburg, Tennessee? Of course, everybody looks at me and go, why are you bringing that up? And I said, well, I have many, many times. The Tennessee Groundwater Association holds their annual convention in Gatlinburg. And I've had the opportunity on many occasions to go down and provide them with some continuing education type training along with several other presenters. But on Main Street of Gatlinburg, if you've not been there, it's a very, very touristy place to be, and there is no shortage of places to spend your money on either side of the street. One of the things that is on Main Street, Gatlinburg, is a place called Ripley's Believe It or Not. It's a museum, right? And I think most of us have heard that name before. And right out on the sidewalk, right outside the front entrance of that museum is this attraction. This happens to be a granite ball, and it's solid. Weighs a little over 10,000 pounds. And the attraction is that these people can come up and they can spin this ball in any direction they want. And they all know that this ball weighs, over 10,000 pounds. This little girl that you see on maybe about 1 or 2 o'clock there, I don't know that she'd weigh 70 pounds, but I guarantee you, without any assistance at all, that 70-pound girl could spin that ball in any direction she wants. And so that's the attraction. And people, they're just in awe about that, and they can't understand why that happens. How can that be? How can a 70-pound girl have any influence over a 10,000-pound ball? Well, if you look down here at the bottom, you'll see this water coming out down here at the bottom, right? That ball is floating. That's what that ball is doing. It's floating. And so when we designed our bottom bearing, very, very similar to that ball over there. Let me give you another example of how about if you a vehicle take a big heavy truck that all of a sudden starts to hydroplane. It starts to hydroplane down the highway. I hope none of you have had to experience that personally, but we do know that happens. And when it happens, it's because a thin film of water has gotten between the rubber tires and the concrete or asphalt. And so those tires are no longer in contact with the concrete and the asphalt. It's like being on ice. You're going to ride this thing out because you have absolutely no control. You are floating on a thin film of water. And so when we brought those segments down, these shoes here, and we lay that carbon bearing down on top, when I say this, I'm pretty proud of this because we were able to create very much the same thing. In other words, we're floating that bearing. We're floating that bottom bearing. And I've asked repeatedly, has anybody ever had a bottom bearing go out on a Flintwalling motor? Have you ever heard of it? And to date, we're years and years removed from the launch date when we put these motors in the market. The answer's been no. And so I think we do a very, very good job with that bottom bearing down there. Well, folks, I'm looking at the clock here. It's 2:55 here in Indiana. This is my last slide. Again, we do these audits, and just as a closer on this bottom bearing here, this is another 24-month audit. And if you look over to the far right-hand side, this was the bearing that we're inspecting under a magnified view. And it says there was absolutely no performance issues, no groove, no cuts, no nothing in that bearing. And I even put here this motor that they pulled this out of was in fact subject to sand and gravel. So I think we've done a great job with that bottom bearing. And so with that, we've just taken kind of a tour, so to speak, from the discharge of a pump down to the bottom bearing. And I believe it's with that then, that this session has ended. Again, I would invite you to join me next month for a couple of these new sessions coming up. Don't forget those handouts that you have sitting on your dashboard. And again, I would always appreciate the time you would take should you give us some response back on that survey. With that all said, everybody be safe. I thank you very much for attending. Look forward to talking to you soon. This training has now concluded. Thank you very much.